right? So good afternoon. Before we proceed with our discussion today, let's do a recap, no, of what we have covered last time. So, can anyone share what they can recall from our previous discussion? Again, are there any volunteers to share with us what they can recall from our previous discussion? You can use the chat box, no, to comment if you have issues with your audio system. All right, thank you, Mr. Plata. No, and with the LU decomposition, we end our discussions on the solutions for systems of linear equation. Okay, and today we will start with the topics covering numerical integration. No, so I think I've asked this before. So this is another checkpoint question. Again, what is a Riemann sum? All right, thank you, Mr. Lukia. So, Riemann sum is a method, no, for approximating areas under a curve. So, this is done using definite integrals, which through which we have to follow the properties referred to as the Riemann integrability, no, and also is rooted on the fundamental theorem of integral calculus. And in this way, we can uh, transform the integration problem into something that can be expressed in summation notation. So, today we'll cover an approach which is aligned to that concept of numerical integration, and this is referred to as the trapezoidal rule. So, this allows us to evaluate the area under the curves by dividing the total area into smaller trapezoids rather than rectangles. And this works by approximating the region under the graph of a function as a trapezoid, and also calculates the area. No? So, like the usual formula for trapezoids, it makes use of the average of the left and the right sum. And the documents suggest that such techniques has been available to us since antiquity. No? So, in a nutshell, if we are to solve for a problem plotted by the blue curve here, so this can be approximated by connecting these 2 points, no, at the function. So the diagonal, including the vertical values of the function at these 2 points or these two reference points, forms the legs of the trapezoid, and the interval becomes the base. And so this provides with this diagonal a better sense of approximation than the previously rectangular methods that we've seen. The shorthand for the formula is presented as this. No? So we are to divide in half or average the vertical values. So we add the vertical values and then cut it in half. And so we average the vertical values and then multiply the base or the increment, no, of approximation. So using a set of trapezoids, you can see here now that this diagram already provides the intuitive demonstration of how the trapezoids provide a better approximation than the rectangular ones, in the sense that the errors in these regions are immediately minimized. Now, to transform the integration into a summation notation, we take on the left hand side values of the function and then the right hand for each increment, and then add them up and divide. No? So this is simply a uh, averaging operation, and then the base is defined as the length of the increment. So the base here and the base here until the end will be of the same dimensional value, and then that sort of addition or sum will go on from 1 to the number of increments that we need. Expanding the summation, then we can have the following. And you can notice that in this expansion, the first and the last vertical dimensions have a coefficient of 1, and then everything in between has the coefficient of 2. The reason is that this vertical dimension here is only used once in the first approximation, but the second one is used in the first and second approximation. Except 2 here is used in the second and third approximation. Except 3 is used in the third and fourth approximation, and so on, no? Until the penultimate section here. Only the last part, and again going back to the first part, do we have the vertical dimensions only being used once. And so the expansion goes like this one. No? And so if we are to automate this process, then we have the following algorithm. So we define the function, the limits of integration, the number of subintervals, then we can have the step size based on these figures. No? You perform integration by defining the upper and lower limit, and then we increment the process, no, and continuously adding uh, some values as we increase the number of iterations. Okay, at the end we sum things up and divide it by the step size over 2, and then we have the integration values. So this can similarly be presented. So this will be the how the codes will look like, no, if you try to implement this. So are there any questions, concerns, or clarifications so far? Okay, so we'll try to present a a sample implementation using spreadsheet. No? So for this particular problem, yeah, no, so I've already run this problem in Wolfram Alpha, so the expected answer should be someone or something close to 460.516. No? So that's the actual output generated by Wolfram Alpha. So in a single iteration, like what is being demonstrated in the slides here, no? So we use a single iteration going from x is equal to 1 and x is equal to 5. So we have a single trapezoid. And so the limits are 1 and 5, and then the dimension is base calculated here, no? As the difference. These two are just simply the values of the function, this equation, at that point, same as this one, no? So it has the same value of the function at this point. And then for the approximate integral will be just be half, and then the h value, and then the sum of these two figures here. Okay, so as you can see, this is the approximate value 666.20 compared to the 460.50 generated by Wolfram Alpha. So if you can mentally project, or you can imagine a straight line being projected from this point up to this point, then this will form a straight line which has a region or a gap between the curve, and that region is your error difference from 666 and 460. All right, so is this clear for everyone? Can I see a show of hands if this example, yeah, is understandable for everyone? Okay, thank you. So maybe you can try to work on this as your exercise, no? So can you try repeating this process, but like this, no? Using h is equal to 2. No? So what happens is that you will split the calculation from 1 to 3, and then another set of calculations will be performed from 3 to 5. So at h is equal to 2, and doing it twice from 1 to 3 and 3 to 5. So I'd like to see your answers at the end now. So you just have to add this up and then come up with the new approximation. And so for exercise, please solve the same problem, but using h as equal to 2, like what is being demonstrated here. So I'll wait for your answers in the chat box. No? So maybe, I don't know, maybe 10 minutes will be 5 to 10 minutes will be good enough, no, to solve for this problem. If you have questions, concerns, or clarifications, then you can post the same in the chat box. All right. Any answer so far for H is equal to 2? Okay, so for those who are able to perform the calculation, please post your answers in the chat box. All right. So any other attempts so far? All right. So thank you guys. Okay. So for the approximate value of that integral between 1 to 5 using h of 2, and so we have the following. No? Okay. So guys, you have to average. I think Miss Mendoza, no, has the correct answer. Okay. Thank you. And good job. Okay, so are there questions, concerns, or clarifications so far? Okay, so if none, can I see a show of hands, no? If everything is clear up to this point. Okay, thank you. So about the others? There's any sort of question or confusion, just let me know, or you can comment in the chat box. Okay, thank you. No, so I guess we can proceed with our next topic. No? So this is a continuation of numerical integration, and this is referred to as the Simpson's rule. No? So it is an extension of the trapezoidal rule, but in this case, the integrand is approximated using a second order polynomial. No? So previously we have the straight line, rather regular geometric approach. No? In this case, we'll be using polynomial or fitting a polynomial to approximate the area. This is the development of which is credited to Thomas Simpson, who made a significant contribution in this field. And it was suggested that an earlier version has been uh, done by Johannes Kepler, no? Which is the same guy who made several observations concerning the planetary motions. No? And previously, he was confronted with the challenge to develop a reliable measurement system for uh, calculating wines, no, in wine trading. So they need a system that is fair in the sense that the equal volumes are pegged against each other. No? So, so one measurement is developed by Kepler, no, to measure actually. So the goal actually is to measure the volume, but somewhat he made significant progress when he has done the area comparison of barrel dimensions. Yeah, no, so for the demonstration, as I mentioned, the curve is approximated using a second order polynomial, and as you know, for quadratic equation, no, we need at least 3 points to properly sample the function that we want to work with. Now, the instead of the usual trapezoid area formula, we have the following expression. So this is the concept of which is somewhat similar, no, to the expansion we've seen in the trapezoidal rule that differs in the last values are only being used once in the calculation process. Whereas these figures in between them are, are used in several iterations. And we have the following coefficient. So to give a more intuitive look at how this process is achieved, then you can see that here for the given function, which we encounter some spikes or noise in, or not necessarily noise, but fluctuations in the values of the function. Then such small or very short in changes are captured better when we are using polynomial for approximation. And so presented here is the first iteration. So you can see 3 points, and that the h dimension or the increment of integration is the half, no, of one sample. Similar in concept is that the vertical values of a and b are only used in the integration, and then these points are used more than twice, no, or the values in between are more used more than twice. And so the coefficient becomes 1 for 1. I'll share a separate link, no, that provides a discussion on how these coefficients are derived. And so later you can see the clips in the links which I provide in this presentation. But this is how simply the same integration process are expressed in shorthand notation. If we try to expand this, and so we have the h over 3 multiplier, no? And the first and the last values are used once, and the figures in between them for the add. uh, coefficients or odd orders, then you have the multiplier of 4. Otherwise, you have a multiplier of 2 right there. Yeah, so you can see, you can check these clips later on how 1 for 1 rule came about. If you try to automate this integration process, then you have to follow the given steps here. No? So we have to define the function and then the limits of integration. The step size is provided by the upper and lower limits and divided by the number of subintervals n. No? And then we start the integration by getting the value of the function at upper and lower limit. Then the iterative process takes place in the mid section where okay, so the integrals are being added, no, in this section, and then the middle terms has this has the integration value multiplied by 2 and then 4, no. Increment this uh, depending on the number of steps defined by the subinterval, and then we multiply by the step size over 3 and display the answer. Okay, so similarly, the codes can be constructed here. No? So this is kind of the same thing as uh, the principle earlier. So we just narrowed this into the relevant uh, process in the calculation. So any questions, concerns, or clarifications so far? Okay, so let's try to work on another set of exercise. No? Okay, so this is the implementation of a Simpson's one-third rule. Now in this case, you can see here no, that the limits are broken down into this. So you have the h value directly obtained from the limits, and then the intermediate value is we'll just divide by 2. Uh, and so you have a point somewhere in between the limits. Then the values of the integration are presented as the following. So the value of the function at 0, 1, and 2 are being used in the first iteration. So for the total, we just have the following, we'll just use the following equation as already provided in the previous part of the slides. So this is for the single iteration. So similarly, guys, I'd like to ask you to try to solve this integral but using 2 iterations. Again, you have to perform integration from 1 to 3 and then another set of integration from 1 to 5. So similar to the trapezoidal rule, the first approximation is at 465, no? So you'd like to see if our expectation is that this will be 465, no? This will be closer in value to 460 if we increase the increments, no? So please try to work on this problem, and I'll wait for your answers in the chat box. Okay, so any attempts so far? Please post your answers in the chat box. All right, so this is the same integration problem, but using the Simpsons one-third rule. So the steps or the procedures are somewhat similar to the trapezoidal rule, but instead we are using the polynomial or 3-point sampling. No, so in this single iteration step, so we have the same intervals 1 to 5, and then we have the h value at 2, no, because we are sampling at 3 points with the polynomial. So here's the value of the function at each of these reference points. Right there. And then the area will be this one, no? 1/3, and then the h value, and then the 1 for 1, no? For the multiplier of these values of the function. Are these steps here clear for everyone? So the the next problem is performing this, but in 2 iterations. No, same problem like what we did in trapezoidal rule. We're using 3 points, but instead you have to repeat this using 3 points. No, or and so we have 1 to 3 here instead, and then this will be 3 to 5. So each value will become 1, and then you have to repeat uh, this process here. No? Right, so this should become 13. And then you should come up with a different set of values for this point. And then add these two figures together, and then you should have come up with an approximation closer to 460. So is the requirement or the problem clear for everyone? So please try to solve now using two iterations. Your preset for this week will be based on the same similar template. Okay. Has anyone attempted? I'll wait for your answers in the chat box. All right. Okay, thank you. So let's check for your answers. Okay, so yes, I suppose everyone has the same answers naman, no? For yeah, so this is for the two iterations, no? Right, so you will be having P sets related to these topics. Right, so for the last topic, this will be the case of the Simpsons 3/8 rule, where the approximation, no, is performed using uh, cubic polynomial rather, no? So the coefficients will be a little different. It assumes the form of 1, 3, 2, and 1. If you can recall from the one-third rule, we have the one for, or the Simpsons one-third rule, we have the one for one coefficient. So this is a little different. And also take note that the leading, or the multiplier here is 3/8, no? Hence the name 3/8 rule. And expanding the series, we can see the following. If we compare this with the basic or the regular Simpsons rule, make use of 3 points to model or plot the function with the quadratic polynomial. No, so we need 3 points. In the Simpsons 3/8 rule, we need 4 points, no, to model the function using a cubic polynomial. Now the steps are somewhat similar in the implementation, except for these intermediate values here, where you have the coefficients of 2 and 3, no, in this point. And so the integration will be somewhat also similar steps. What differs are the coefficients in the middle, no, and that again we're using 4 points instead of 3 points. Okay, so not included in your activities, but just to right, so just to give you the idea that if you're confronted with integration problems, which are which which are of the nature of data points having unequally spaced data points, no? So you can use combinations of these approaches, no? Like in this case, if you have a rather irregular surface to solve, you can use the first one. For the first one, the regular trapezoidal rule. In the second point, you can use the regular Simpsons rule, and then the 3/8 rule afterwards, no, for a much more fine tuned approach to the approximation problem, and then go back to the 3/8 rule, or the regular one-third. And for the other parts, again, you can go back to the good old trapezoidal approximation. Okay, so you can use combination of these methods if you have a rather irregular forms of surfaces to solve for. So just saying, no, that it depends on whatever approaches suits your requirements best. So you'll be having another set of projects related to this. So you can refer to online sources as well. for some examples, no, of these integration problems. Right. So the first one is again the group project uh, for the integration. So you'll be given 2 weeks, no, for this, and again this will be done in groups, no. So you can use Python, uh, preferably in form of collab, no. So you can work on this problem in a rather collaborative manner. Okay. Okay. So I posted the guides for the group project too. Kindly check in the classwork page. And also your PSET 9, no? For your PSET 9, you'll be working on the same problem. Uh, this will be done in a spreadsheet or any or in Excel or any spreadsheet application. So you'll just kind of extend the exercises that you've done earlier, but using 8 iterations for trapezoidal rule, Simpson's rule, and then the Simpson's straight rule. Okay, so can you say show of hands if you were able to access the instructions for both PSET 9 and Project 2? All right, thank you. So are there any questions, clarifications, concerns or clarifications so far? Okay, if none, again, can I say a show of hands, if everything is clear up to this point? Okay, thank you guys. No, so I've seen some follow-ups on the project matters. No, I'll try to address this uh, sooner, no, so you can proceed with the implementation. So just wait for my response. No? I'll try to address this within a day or 2 days or 3 days. Okay, so I'll check your follow-up inquiries, no, regarding the project. And similarly, if you have further concerns or questions, I can just for the other groups, no, you can just respond on the email thread that we have, and also similarly, I'll try to address your concerns and questions. So these slides will be uploaded later for you to refer to in your PSETs and projects. And I guess that's it for me this afternoon. And I'll see you guys next week. No? And have a great week ahead and stay safe.